Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
The U.S. annual cost of software errors was more than 0.5% of the GDP. That's a lot of money. Once software has shipped, it's anywhere from twice to 30 times as expensive to fix a bug. So wouldn't it be great, wouldn't it now, if we could fix problems in software before they ship? The traditional approach to doing just that is testing, right? Testing requires good test cases, but it can be very expensive. These days, up to 50% of a commercial software project's development budget can be devoted to testing, maybe more at scenic local locations, right? And testing is great, but it doesn't catch all the bugs yet, although maybe given a few more months, Tom and his buddies will fix up that problem. An alternative approach is to use program analysis, and that's the sort of thing I'll be talking about in this talk. We systematically look at the program and see if it's doing the right thing and point out potential bugs if it's not. Traditionally, the world of program analysis conveniently divides into two disjoint areas, although it's handy when you can combine them. The first is dynamic analysis, which I would liken to running on the doctor's treadmill where they put all those wires on your body, right? You attach sensors and instrumentation to the program, and then you run it on some indicative or perhaps synthetic workload, and you report if anything bad happens. Or if nothing bad happens, maybe you get a better idea for the normal behavior of the program. And purified gprof profiling eraser for finding log mistakes. These are all great examples of dynamic analyses. The other approach, traditional approach, is static analysis. It's kind of like applying for car insurance. You call in, you tell them if you're married or not, how old you are, what your zip code is, and then they try to guess how safe you are without ever actually seeing you drive. Right? So here we look at the source code, and we, I like to believe that static analysis is more fun than actuarial tables, but you know, we never know. You'll see how well I support that in this talk. So you simulate running the program, and SLAM, or the Static Driver Verifier now, the Coverity project from Stanford, even the humble lint are all great examples of static analyses. Okay. Bad news for me and for many others, in order to find mistakes in the program, you need to know what the program should have been doing, maybe some formal notion of a specification of its behavior. But even if you have that, the problem is undecidable by quick reduction to the halting problem. So it's sort of traditional to abstract away some of the, yes?
Enough to know what the program should not be doing, like it should not be dumping core.
Yes, yes, and you can get a lot of mileage out of implicit specifications in language like C. You shouldn't dereference a null pointer, right? And I'm in fact going to be concentrating on that sort of partial correctness. I'm not going to try and prove that your web server is a web server instead of an FTP server, but I will want to make sure that it uses database locks correctly, that kind of thing. All right, so once we abstract away part of the program, maybe some of the data, maybe some of the control information, we're typically left with an approximate analysis. Does this program violate this specification? We might end up being either unsound or incomplete. We may fail to find a bug. We may say that OK code is buggy, or horror of horrors, we may do both, but we'll try to avoid that. Okay, this is what I believe. This is the controversial portion of the show. I believe that static analyses are very good at finding bugs, and actually a lot of those projects are in this room now. And I think that instead of better answers to the questions that we already have, like how can I find more bugs in programs, we need better questions. Like what should the program have been doing? Or how can we explain the bugs that we found to the programmer in such a way that they actually get fixed before the next version? How can we help the programmer fix the bugs? Is there something we can do at the language level to make this easier? Is there something we could have done to have prevented an entire class of bugs by outlawing certain constructs or by making certain things easier to do? Okay, so what am I going to be talking about in this talk? As a concrete example of a class of errors, I'm going to talk about how programs handle exceptional situations and possibly make mistakes in the presence of these exceptional situations. I'm going to claim that this is at least a non-trivial part of program reliability, so it'd be handy if we could fix up things here. I'm going to present a static analysis and a fault model, a data flow analysis, for finding mistakes of this sort in programs. And then, after that, I'm going to propose a new language feature, which you won't be tempted to use, to fix up this sort of mistake. Right? But I'm going to try and convince you that it wouldn't be too painful if you were to use it anyway. After that, I'm going to talk about some work I've done in specification mining to try to automatically infer desired program behavior from traces, either static or dynamic traces of the program. And then I'll talk about a bit about what I'd like to do in the future and what I believe about PL research. So by way of analogy, let's imagine that you are, because these terms like runtime error handling, mistake can be sort of difficult to follow. Let's imagine that you're cooking a large meal for a bunch of people. You've taken this pot, you're filling it with water, you take this turkey out of the freezer, you're putting it in. This doesn't work in Berkeley because you never have to defrost tofu, right? Your friend calls and says, oh, I'm in an auto accident, can you come pick me up? You rush out the door to pick her up, but you've left the faucet on and the freezer open, right? And now some bad things happen. Maybe the kitchen floods, maybe your frozen food dethaws too early. This sounds great, but does this ever happen in the real world? Yes, in the real world, you might be an e-commerce application updating an inventory table for some remote shopping cart purchase, right? These are important resources you have to deal with. Some sort of exceptional situation happens. There's a network timeout on the client talking to you, right? You stop to do something to handle this error in an application-specific manner. Maybe you want to write a log record so that the system operator can take a look at this behavior later, right? So you jump to this exception handler. And, crushing blow, you forget to release this lock you had on the inventory table. And this is bad perhaps because it lowers transactional throughput with other things sharing this external database. That's the sort of runtime error handling mistake, exceptional situation mistake that I want to find. Okay. So in this talk, an exceptional situation is not, in fact, a bug in your code. It's something sort of in the environment that you should be wary about if you want your program to be ironclad, but that might happen to anyone, right? Maybe there's a network connectivity problem. You're on a wireless network and one of the packets are dropped. Maybe there's a database access error. You're using opportunistic concurrency control and someone else has written and committed a value that you've read. Maybe the operating system is out of file handles. Happens every once in a while. When these sort of exceptional situations occur, the program often has, we hope, some sort of exception handling code, right? Maybe if the packet didn't get through on a UDP network, you try resending the packet a few times. Maybe you show a dialog box to the user. That sort of code is application specific, and I won't be able to check it for correctness at all, at least at this point. I'm not going to check and see if you're opening the right dialog box. However, it's possible that in the process of resending this packet over the network, you end up mistakenly leaking a database lock. That's the sort of mistake I'll look for. Okay. So I spent a while trying to narrow down what I mean by exceptional situations and program behavior in that regard. It's sounding sort of complicated. Should we care about this at all? Maybe there are many other fruitful areas to look for bugs. Right? Turns out that a lot of program text can be devoted to error handling. An old IBM study suggests that up to 2/3 of a program can be devoted to handling exceptional situations. That number seemed really high to me, so we tried to reproduce this study on modern open source Java programs. We looked at 4 main lines of code and found that between 3% and 46% of the program was related to handling exceptional situations, and that number scaled with program agent size. So these sort of older, more mature programs, closer to 46%. 2-week-old student programs found on the web, closer to 3%. Right? So a lot of this code is error handling. Is error handling important? Yes. Here's one concrete example. Mistakes in which applications don't properly handle error conditions that occur during normal operation are listed as one of the top 10 causes of Java web application security risks. So a lot of your code is devoted to error handling, and if you make a mistake there, it can hurt you a lot. Yes, Tom?
Did you ever think of actually using code coverage as a way to identify exceptional state? The idea being that people are really good at writing text for the segregation but not at the exceptional cases. So with code that's not covered is more likely to be error handling.
Yes. Okay. So, and everyone can hear the question, so I won't repeat it. But so I did think about doing this, but it turns out that at least in this particular application domain, it's not as indicative as I would have liked. Often it turns out that there is error handling. The problem isn't that you forgot to have an error handler or some such, but that the code that you want to have just isn't there. It's not that you have a conditional if star, then sometimes I release this lock. It's that entire line is missing. So there's no line with low coverage that I could point to and say, this is indicative of a mistake. Using code coverage could help me identify error handlers, but in languages like Java or C#, they're delineated by special syntax. So it was tempting, but it didn't work as well as I might have liked. Does that answer your question? Yep. Yes. Okay. Yada. So there's a lot of this stuff, and if you get it wrong, it's really bad, which means it's particularly depressing to take a look at the state of the art and see what's out there. So I did a survey of all of the catch, finally, and finalize blocks in 4 main lines of open source Java code, and I'm sure that Microsoft managed code is much better than this, but when I looked, the 2 most common exception handlers were my personal favorite, number 1, do nothing. This is open brace, close brace, the exception handler that notices the error, respectfully doesn't do anything about it, and then continues on. Second most common, prints the stack trace and aborts the program. This is handy perhaps if you're developing and debugging, but not so great once you've shipped. I believe that higher level invariants should be restored, interface requirements should be respected. Aside from handling the exceptional situation, the code should clean up after itself. Okay, but I've said should a few times here, and I want to be a little more formal about what I mean. One common approach, especially in this neck of the woods, to describing at least partially what a program should be doing or what the program shouldn't be doing is to express a safety policy as a finite state machine. And here I've got an example safety policy governing Java streams, much easier than the sort of IRP handling policy that one might put up. The intuition is that we have one finite state machine per stream object dynamically in your program. You start in the start state. Every edge represents some important event. I make a new stream, I read and I write for my stream, eventually I close it, and hopefully at the end of the day, we're in an accepting state. And if we're not, then we say that the program has violated the safety policy in that regard. Even this simple sort of two-state, three-edge safety policy, too complicated for the purposes of this talk, we will pare it down to this very simple two-state, two-edge, open-close, malloc-free, acquire-release sort of safety policy. A lot of common behavior is captured by this. Later on, when I talk about specification mining, I'll talk about learning possibly more complicated or application-specific safety policies and fitting them together like Voltron. But for now, we'll stick to this simple model. Okay. So now that we have a more formal notion of what the program should be doing and what's actually happening, well, I'm going to claim that it's difficult for programmers to consider all the possible execution paths in the presence of exceptional situations. That is, it's difficult to imagine all of the things that could go wrong at once, and therefore you don't have code to cover all of these corner cases. So we're going to find that there are a few paths related to exceptional situations in which some of these important safety policies are violated. So let's see a concrete example. Oh, this concrete example is much too scary. Let's abstract it away to something that does all of the same things but is sort of only 6 lines long. Right? So here's simplified Java code from the Ptolemy 2 project at Berkeley. And I'd like to thank Christopher Highland Brooks for letting me use his code in public and point out mistakes in it. Very generous of him. How does this code work? Intuitively, it's sort of simple. We make this stream at the beginning. We make this new output stream. We go around this while loop a few times, copying data from the input stream to the output stream. And at the end of the day, we close both of our streams. So it looks great. It looks like the programmer has been paying attention to our stream safety policy. We made new streams, but we're careful to close them at the end of the day. However, in languages like Java or C++ or C#, it turns out that there are at least 4 places in this innocent-looking piece of code where exceptional situations can cause you to violate this safety policy. How does this work? Well, we make the new input stream. Let's say we make the new output stream. But somewhere in the middle of this loop, something goes wrong. Maybe we're reading from the input stream over the network, and there's a timeout. Maybe we're writing to the disk, and the disk is full. Control will jump in languages with explicit support for exception handling to the nearest enclosing exception handler. There isn't one here, so we'll peel some records off the stack and eventually get to one. But since the input and output stream were local variables and we never put them anywhere, we lost any way we had of referring to these objects until possibly the garbage collector gets to them at some much later point. So we'll never execute the statements to close the input and output streams. Given that language-level error handling sort of caused this problem, we might be tempted to use language-level error handling to fix it. Oh, couldn't we use a try finally statement here? Yes, perhaps. How does try finally work? You execute all of the statements in the try block, and then, no matter what happens, regardless of whether you get through them all successfully or there's some sort of unexpected error, you immediately jump to the first statement of the finally block and start executing at that point. This sounds great. Now, no matter what happens, we'll try and close that output stream. But it turns out that we've made life worse for ourselves. Now there are at least 5 places where something can go wrong. That will yield some sort of exceptional situation where we will violate this safety policy. How might this work? Let's imagine that we make the new input stream, but we go to make the output stream, and maybe you're trying to write to a directory you don't have permission to. Maybe it's a network stream, and you've given a bad address that doesn't map to anything, right? So that bit doesn't work. So as we said, we jump to the beginning of the finally block, and we try to close the output stream. But since we never assigned the output stream, it's null. So we're doing a dispatch on a null pointer. So we jump out of the finally block, never getting to the input.close statement. And this is the sort of concatenation of exceptional situations that it's difficult for programmers to reason about or to remember to do the bookkeeping for, right? Well, is the world hopeless? No, in fact. You could handle this in an ironclad manner by using nested try-finally statements, one for each important resource that you're juggling at the same time. Right? This works out pretty well when you have 1 or 2 resources. For the programs that I'm going to look at, we're going to have 3 or 5 resources, and for whatever reason, software engineering disadvantages, programmers seem not to like to use 5 nested try-finally statements, perhaps because the indenting gets too far over to the right. Maybe there's a more formal reason, right? You might also be tempted to use runtime checks. This is sort of idiomatic in languages like Java, at least. In C# you could use destructors to help yourself out here. Here we set input and output to these special null sentinel values at the beginning. And finally, at the end of the day, if the output is not null, then we assume that we've successfully allocated it. So we try to close it, being careful to catch all of the exceptions that close could raise. Bonus points if you remember the exceptions that close could raise. And then we do the same things for input, right? And this looks good, but it's difficult for programmers to keep track of this bookkeeping to do it correctly. And it's worth noting that at this point, this blue exception handling code is a big chunk of the program. In fact, we now have more exception handling code than we have original code, and all of the control flow here is to deal with exceptional situations. Right? This happens, but it's inconvenient. Okay. So I've claimed, or I've tried to demonstrate sort of intuitively why it's difficult to write ironclad exception handling, and I'm going to present a static analysis to find mistakes in exception handling to back up the claim that this is tricky. Okay. Once again, whenever I want to use a program analysis to find mistakes in a program, I need a formal notion of what I should be checking for. The first time, I will give these by hand. Later, we'll try to learn them automatically. Took a survey of Java code and checked to see what are programmers actually closing, what sort of generic resources that are in the standard libraries so that I can apply these specifications everywhere. We settled on sockets, operating system file handles, streams, and locks with external JDBC SQL databases. And in general, these are all sort of simple two-state state machine safety policies, aside from the database one, which is a bit more complicated. Yes? Yes, I will. I can skip there now if you'd like, or okay. Okay, I will certainly say something about finalizers. It will appear in the title. When I do, raise your hand again, and I will say a bunch of things about them. Okay. So I think that the program should be very careful of these resources along all paths, even in exceptional situations. Unfortunately for me, exceptional situations are rare. That is, it's difficult to just construct test cases that will expose bugs in error handling. You might come up with a special test harness that says something like, oh, I will have every fifth call to fopen fail, but people tend not to like those because in some sense they're unrealistic. You see them very rarely. So, yes?
So, is it a good time to ask you the second question?
Yes.
So, why isn't the solution to this just to build a control flow implementation that models all the exceptions control flow and detail-based defect detection tool that goes through all paths with these sort of prototype?
You're going to see me doing this in just a bit. Okay. And then perhaps we'll add on to that in a second. So, as Manavir suggested, we're going to try and build a control flow graph that models exceptional situations, right? One of the tricks here is that this is slightly more complicated than it appears at the outset. We want to have reason to believe that exceptions at the language level are actually correlated with exceptional situations or real runtime errors, right? So if we're in a language like F#, then you might be using an exception like not found as a way to have local control flow and jump out of a loop, right? And I don't want to mistake that with exceptional control flow. Turns out that there are certain exceptions in Java and certain exceptional situations that are highly correlated, right? So if I'm a Java program making a remote method invocation across the network to some other server, and someone else hits the other server with a hammer and causes it to catch on fire, I will notice this locally as I try to invoke a method, and instead of it terminating normally, it raises one of its declared exceptions, at least among a certain subset of important ones. So my fault model for generating this special control flow graph is that a called method can either terminate normally or raise any of its declared exceptions. Once I have this, I build the control flow graph, and then I'm going to symbolically execute each method in turn, abstracting away most of the data values, but keeping track of outstanding resources in the standard sort of type state over control flow graph method. Nothing new here for many of you. Despite that, I feel sort of compelled to show an example. Here's my simple 3-line program. I make this new socket. I send an HTTP request. And loosely, the problem is that the close should be in the finally block. If something goes wrong with the send, we might leak this. I build the control flow graph, and shown in red are the special edges that I've added in to handle exceptional control flow. Along every edge, I want to keep track of what state in the state machine the important resource is in. Initially, this is an intra-procedural analysis, and we'll get to whether that's a strong disadvantage or not later. We don't have any outstanding resources. If I successfully make the new socket, then I have an obligation to close it at some later point. If I don't make the new socket, then no harm, no foul. If I send data over the socket, then I should still close it later. And in fact, even if the send temporarily fails, maybe it's a wireless network, temporary network connectivity problem, I should still close the socket later. If you close the socket, then you've discharged your obligation. And in fact, even if closing the socket fails, we'll say that you've discharged your obligation because no one writes a while loop around close until it succeeds. And the object of this sort of analysis would be to find a path from the start to the end where on the edge going into the end node you have an outstanding obligation, kind of like this one. And then you would report it as a backtrace sort of thing through the program. You start on line 1, you go to line 3, you take this if statement, and then you make a mistake. Later on, I'm going to claim that that's not as handy or not as sufficient as I might like, that we need better ways to explain these errors once we found them. Yes? Yes.
Who made the decision that if the close fails, I'll discharge the application from using a manual thing? Or it's part of the spec in some way? Or
It's part of the specification in some way. Here's my rationale for it. It is my personal belief that it's very important to have the developers or the final end user trust the output of the tool, right? So when I was building this control flow graph annotated with exceptional information, in languages like Java, there are unchecked exceptions for things that could go wrong, like the JVM suddenly dies, or your division was actually a division by 0. I didn't include them, even though they're possibly valid, right? So I might well have been able to find more errors in programs if I said, oh, let's imagine that all of your divisions are division by 0. But often there's external reasoning, things I'm not modeling, where the programmer would say, no, in fact, I know that this division will never be division by 0, right? Especially if I'm abstracting away data values, they might even have an explicit check there that I'm not going to see. I would rather have all of the reports coming out of my tool be trusted and miss a few bugs than the other way around. Right? So conscious decision on my part to say, even if close fails, you've discharged it. Okay. Also, in practice, I never observed anyone checking the return value of close. Okay, so if you implement this as I sort of naively described before, the short version, then the analysis will find all potential bugs with this specification, but it will yield a bunch of false positives. In particular, if I were to give you 100 error reports, say 70 of them would be real bugs and 30 of them would be false positives. I would say that this part of the code has a mistake, but in fact it does not. In my experiments, which I'll show in a bit, each one of the false positives fell into one of 3 easy categories, perhaps because this domain is sort of idiomatic. One was to check the resources we've acquired against a special value, like null, and if it's not null, then try to close it. Since I abstracted away data values, I'm going to miss that correlation. Another is to store an important resource in the heap or in an object field in an object-oriented language, and since I didn't say anything about alias analysis or modeling the heap with some special shape analysis, I'm going to miss this correlation. And finally, it's very common to write special wrappers around allocators. Maybe you're allocating in your own array. Maybe you have some special logging functions you're doing. And since this is an intra-procedural analysis, I'm going to miss that correlation. Right? Okay. So I was now tempted at this point to consider, oh, is it worth my time to write an inter-procedural analysis and do context-free reachability and do the balanced parentheses matching, build procedure summaries, right? In this particular domain, one reason that it's not is that the call graph is actually very hard to come up with. I looked at, for example, some Java Bean programs where you have components that are assembled at runtime according to interfaces, and then a request is fed through them. And it's not clear without this runtime configuration information what a call actually goes to. But another is that I did an experiment to quantify exactly how much I'm missing by not having an inter-procedural analysis, and it turns out that here it's actually pretty low. So if I instead filter out error reports that would contain one of these 3 forms, or more specifically, if there's a path that passes through an if socket is not null, socket closed, then I would remove an outstanding socket. If the set is now empty, then I don't report anything. If I filter those out, then now I'm going to introduce false negatives. My tool will now fail to find some bugs that are actually out there in the world. And based on 2 random samples, for every 100 real bugs that we report, there are about 10 bugs that we miss. Okay. This removes all false positives in practice, and for me, this trade-off is worthwhile. We're going to see that I'm not going to be able to get developers to fix all of the 100 bugs that I can point out, so finding 10 more would not be handy. I manually verified the rest as bugs, which took loosely forever. How did this turn out? Here on the left, I've got the program name in Java. These are all open source Java programs, and then the lines of code. The blue exciting column in the middle, the one I want you to pay attention to, is the number of distinct methods with exception handling mistakes. We've seen before that there can be 4 or 5 paths out of a method where you leak something. We count each method only once. And finally, on the right, we have the primary and secondary forgotten resources. Right? So in general, we looked at 4 million lines of Java code, found about 800 methods with exception handling mistakes. And in general, Java programmers were leaking operating system file handles and database locks. Yes, sir?
The 18 others together have only 180 mistakes. Are they much cleaner? Are they much smaller?
They're much smaller, right? So one figure that I didn't include here for simplicity, but perhaps that I should have, is that not since my specifications, my important resources were kind of generic, sockets, database locks, not all of the programs use them equally. For example, in Eclipse, it's a large program, but only 10% of its files even mention any of the resources that I'm talking about. So from my perspective, it looks like, or from my analysis perspective, it looks like a smaller program to some degree. The smaller a program is, the greater fraction of its code is initialization or GUI or whatnot in this domain, and less of it has to do with sockets that I can check. Sure, yes. It's astonishing the code is. I will try to argue to you that the code is not actually that good. It depends on what you mean by low or high rate. Typically, Yeah, yes, I would get.
So, a parking question. What three methods
Okay, so I don't have this number for you off the top of my head, but based on the ones that I looked at, I would guess 120 lines. Yes. Yes, sir.
Even in a chance, never open socket, never close socket.
Right. To some degree, some of this depends on the call graph. You might not open or close a socket yourself as a method, but if you have an uncaught exception, imagine you're trying to talk to the database and you make some mistake. That exception might propagate through you and through your caller, who was dealing with the socket, all the way up to someone above that. Right? Difficult to measure without dynamic traces. I'll talk more about dynamic traces in a bit. There's still a question hiding. Yes? Yes. Let me go back and give a concrete example. This code here, this is the real Java code from which I abstracted away these 6 lines. Right? It turns out that there are about 4 places where if an exception occurs, you will leak one of these streams. Right? Here, at this read, at this write, and at this close. There are 4 ways to get out if you're leaking something. I count this entire method as 1 on that table. This whole thing is 1. All right. One answer is that I don't see that very often because of the way exceptions work. It's actually very difficult for 2 methods to collaborate and raise 2 exceptions at the same time and somehow have them merge. I will charge the method that first sees the exceptional situation or the runtime error, not other methods that the uncaught exception might pass through. Okay. Yes. 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 And in general, I want to present the most conservative figures I can in order to have everything I say be believable. Yes. So I could have counted it 4 times. No, we're going to count it once. Also often because if you would do one fix to this procedure that would close all of those 4 ways to leak with a single resource. Okay, yada yada. Back on the magic table. Other questions about the magic table? Okay, so we claim to find 800 bugs. I'm going to claim that that's a lot of bugs, although of course error counts vary. Rather than sort of showing you 800 different instances of developer code, I'll try and summarize what we saw. I had to look at all of these to verify that they were real bugs. Right? So let's imagine that some important resource allocation AX, like open, must be followed by some cleanup code CX, like close. What did we see a lot of? Well, we'd see within one method, we'd acquire an important resource and then free it using iron-clad error handling. And then just a few lines down, we would do the same thing, but with no care for exceptional situations or runtime errors. It's also common to see multiple nested resources within one try finally statement. And as we saw before, there are 4 or 5 ways where that can go wrong. Every once in a while, we'd see programmers acquire 2 different resources of the same type, like 2 locks, and only remember to free one of them in their iron-clad error handling. Difficult to imagine that this code ever worked well at all, but it's out there a lot. Finally, and most insidiously, this is how we see the heap coming into play. Often we'll see programs go through a list, iterate over some sort of enumeration. For every element in this list, we acquire a lock, do some work, and then release the lock on that element. If somewhere in the middle of this there's an exceptional situation, we'll leak a lock on the middle of the list. That's a deadlock waiting to happen, but none too soon. Right? We also see quite a bit of tricky flag work for getting rid of this stuff early. If you've got a database lock, it's like this hot potato. How fast can I throw it away to somebody else? I don't want to be holding on to it. And we'll keep track in Booleans. Have I already closed it? If not, then try to close it now. If not, try to close it again later. Turns out that programmers can make mistakes in this bookkeeping. Okay, so what would we be tempted to do to avoid this? Well, you might want to use language level features for keeping track of resources. And finalizers, ask me again, right? So in general, you might be tempted to use destructors, especially if you're in a language like C++ or C# that actually has destructors. I like destructors. They are great for stack allocated objects. How does a destructor work? It's a method associated with a class, and whenever an instance of that class goes out of scope, if it's a local variable, the destructor is automatically called. Right? This works great. If your object is in the heap, then you have to remember to call delete yourself, which is sort of like remembering to call close, which we've seen is sort of tricky. One downside of destructors is that the error handling code has to be declared in some sense away from the use or the instance of the error. Right? Error handling, we'll see in a bit, often contains unique or arbitrary code. For example, in this undo program I'll use in a case study, there were 17 unique cleanup actions, one of which was 34 lines long. If these cleanup actions reference local variables, then those variables have to be made global in some sense, or class level, protected, or friends. You might not want to do this for software engineering reasons, right? Or you might have to make up dummy objects, and sometimes people do this with auto pointers or whatnot, specifically to handle your cleanup code that are there only to make sure that the destructor is invoked if exceptions occur. So from a software engineering perspective, it's not as convenient as you might like, although it's very powerful. You might also be tempted to use finalizers, although actually I'm going to claim that you won't be tempted to use finalizers because they are widely reviled. Everybody seems to hate them. A finalizer is a method associated with a class, and when an instance of that class is declared unreachable by the garbage collector, which may or may not happen, the finalizer is invoked. Right? So they're called by the garbage collector, which is deemed too late. If I've got this important database lock, I don't want to wait for the garbage collector to find that it's unreachable. More telling from my perspective, as sort of a I wish I had a type system guy, is that there's no ordering guarantees in finalizers. If I have a socket and then I build a stream on that socket and those two things are collected in the same sweep, we can call the socket finalizer before we call the stream finalizer. The stream finalizer might try to refer to the socket. That would be bad. Bonus points if we resurrect objects, right? The most telling thing I can say about finalizers, though, is that no one uses them. This has to be the most underutilized language feature I've seen. In 4 million lines of code, I found exactly 13 user-defined finalizers. And you might say, well, maybe application code isn't supposed to be using finalizers. It's for people writing libraries and data structures. So I took a look at the libraries. I took a look at the GNU version of the Java standard library and Sun's version. For those 4 important resources that I mentioned earlier, socket, streams, database locks, mumble, they each had 2 finalizers that were for not quite sort of overlapping sets. So you can't portably count on the underlying system to save you with finalizers, and it doesn't occur as often as you would like. Okay. What are you left to do, poor programmer? Well, one thing that we see quite a bit is to use tricky flag work. Can I just throw more code and more logic at this problem to make it go away? Yes. So here's this integer flag f that tracks how far we've gotten through this procedure. This is adapted from actual code I ran into. Right? We acquire resource x, we set the flag to 1, we do some work. Acquire resource y, set the flag to 2. Let's imagine that there's a problem now. We jump through to this finally statement, switch on f, we close y, we fall through, we close x, we get out of there, right? This is fine. Maybe, but it doesn't scale very well. As soon as you add any non-trivial control flow to the top half of this block, you have to remember it down there in the bottom. And if instead of an if statement, this were a while statement, we'd have to remember how many times we went around it. And it turns out that humans aren't very good at doing this bookkeeping by hand. Wouldn't it be great if I could somehow do this bookkeeping for you and remember at runtime whether or not you had allocated resource Y? Huh. Yes. Ah. Yeah, my code. Yeah, I don't think the original code has that mistake. I think my abstraction has that mistake because I wanted to fit it on the slide and I forgot. Yeah, that's very nice. I forgot this missing default. Okay, fair enough. Yada. So what can we do about this? Well, wouldn't it be great if I could propose some sort of language feature that would make the world a slightly better place? Okay. So what we want to do here is make it easier to write programs where you avoid forgetting these important obligations. If you acquire a database lock, you don't want to be holding on to that for a long time. But I don't want to add any static restrictions to how you write your programs. In some sense, I have vault envy. I would love to say, oh, we can solve this entire problem with linear type system. And in fact, we can. But then it becomes very difficult to write general programs, in some senses, maybe autofocus and adoption save you, or to store important resources in complicated data structures. I wanted to make this look as much like existing Java or C# programs as possible to make it easy to adopt. Right? I want to be able to take advantage of optional lexical scoping. If you've written your program in a way that destructors would be well suited to, I want that to work. However, I also want to allow you to do cleanup actions early, if you so desire, and have arbitrary cleanup. Right? So for my semantic backing, I'm going to steal notions from the database and workflow communities, the notions of the compensating transaction and the linear saga. Loosely, if we view your program as sort of spitting out a series of important events over time, I either want all of your actions to succeed, or you get sort of halfway through, A1, A2, then there's some sort of error, and then you clean up everything in reverse order. Clean up 2, clean up 1, right? Respecting dependencies. Okay. As soon as I mention adding something vaguely transactional to programming languages, you might well be tempted to use any of the other great pieces of work that do exactly that. Right? This has been a fruitful area of research for many years. I'm going to claim that, in some sense, pure transactions are too heavyweight for many programming language tasks. For example, often you're willing to forsake consistency or durability. More tellingly, in languages like Java, say, when you do want full ACID semantics, often you make calls using inline SQL to some external database that will provide just that for you. Right? But for handling your program-level mistakes, that might not be right. Why? Because handling these errors often involves conditional or dependent activities. I have to check this local variable. If I'm in state 1, then do this. If I'm in state 2, then send this snack packet. And for that, you'd want some sort of advanced transaction model, like compensating transactions. How do I undo the effect of this after it's committed? And that's what I'm proposing. I also claim that in some sense, directly adding transactions is a foreign programming model. Now you have to add begin and end transaction to your program, and it's not necessarily clear to the programmers how you abort a socket send after you've already done it. These problems are well understood in the database community, and in some sense we know the answers to all of them, but I'm going to claim that avoiding it makes it easier to adopt this sort of change. I'm also going to claim that changing things at the language level is orthogonal to having, say, failure transparency through checkpointing and recovery or duplicating the hardware in the background. You can make things more reliable by duplicating the hardware and by making the program better, and you can multiply them together. Therefore, I propose, in my world of unimaginative names, the compensation stack. I think you should store cleanup code in runtime stacks. These are first-class objects, and you can pass them around. And in general, after any important action succeeds, I think you should push the cleanup code onto the stack. And here, action and cleanup can be arbitrary code. We'll add anonymous functions to Java. At some later point, you pop all the cleanup code and run it in last in, first out order, either when the stack goes out of scope, or if there's an uncaught exception, or early when the stack is finalized. Right? And at the end of the day, these compensation stacks end up looking like generalized destructors. You don't need to make up special classes in order to do local cleanup. You can call them early and we'll do the bookkeeping for you. You don't need to keep track of Booleans or integers. And you can have multiple stacks. You might imagine having one for each request in a web server, and if something goes wrong servicing one request, you don't want to invoke the error handlers for the other request. Once I have them, I'll add annotations to interfaces to require them. I'll be evil and say, oh, you can't even make a new socket without promising that you'll put socket.close on some stack of obligations, on some to-do list you're carrying around. And through a combination of a static type system and some runtime checks, I'll make sure that you remember these obligations along all paths. What does this look like in practice? Here's my 6-line example from before. Imagine that I wanted to make it look as ugly as possible using compensation stacks. How would I do this? At the beginning, I've made my new compensation stack object, and I've wrapped the entire thing in try finally. Somewhere in the middle, when I'm acquiring this new input stream, my important action, if it succeeds, then I push onto this compensation stack CS input.close. It's possible that we'll get all the way here and acquire this new output stream. If that succeeds, then we push output.close onto the stack. Finally, at the end of the day, we pop everything off the stack and run it. Right? So no matter how far you get through this procedure, you close exactly those things that you've opened. I mentioned before that I would annotate the interfaces. So here, rather than remembering to call this.close yourself, the stream constructor has been changed to accept a compensation stack argument, and it, if it succeeds, pushes this.close before returning onto that stack argument. Now, in some sense, this is a minor software engineering benefit. The client does not have to know individual cleanup code routines for different objects. They just talk to the compensation stack. Once I've done this, it's going to be common to pass in a compensation stack, a single one, to a function that previously didn't expect one. So if you so desire, as a flag, I will automatically pass in the most recently declared lexically scoped compensation stack. Right? And finally, if it turns out that your resources are bounded by the stack lifetime, if they're lexically scoped, then, if you so desire, I will allow you to use an implicit current scope stack that's declared conceptually at the beginning of the method, and finally, at the end of the day, we run everything on it. So here, if you're willing to let me take your life in my hands, if you trust me a lot, this code looks just like the code from before, except that it's slightly shorter because you don't have to call close. But no matter what happens, no matter how far you get through this, I will close and clean up exactly those things that you allocated. Okay. It's easy to work on 6-line examples. Does this work on something slightly more evil? This is our if this switch statement sort of thing from before. Can I rewrite this using compensation stacks? Yes, and I claim that it makes the structure a bit more explicit. Here we're again using this current scope stack, but this time I've left the compensates in. So we do X, we do Y. Notice that the if doesn't have to be duplicated. If we end up actually opening Y, then we push Y onto the stack. And then finally, at the end of the day, we run all of these things. Okay, well, It's very easy to make PL features on the whiteboard and claim that the world would be a better place if you were to actually use them. But I want to back up that claim a little more seriously, so I actually implemented these. I extended Java to support these compensation stacks. And then I annotated some key interfaces, the 4 from before, files, databases, to use them. And then I took 2 existing programs and changed all of their error handling to use my compensation stacks instead of a standard try finally, right? Both for these library resources and for any sort of unique application-specific cleanup actions that they had. It's worth noting that I didn't add any new exception handlers, even when I saw places where they could have gone. And then I did 2 case studies, one to test the expressiveness of my feature, can I handle a lot of tricky cleanup, and one to look into possible reliability gains, because it's easy to forget in the middle of the story. My actual goal here is to improve software quality and reliability by finding and fixing bugs, right? So if I'm fixing things but the software isn't getting better, then... So my first case study was Aaron Brown's undo program, which claims to provide operator-level time travel. I wish I had that, but is actually a networked logging SMTP and IMAP proxy. It's about 35,000 lines of code, and there were about 130 places where I changed his error handling to use compensation stacks instead. His program was sort of tricky. He had 3 to 5 step linear sagas, that is 5 resources at once. You would have needed 5 nested try finally statements. And his cleanup actions were themselves very complicated. They had their own internal exception handling and synchronization, right? So I figured if I could handle this, I could handle many things. As a result, at the end of the day, the program was about 1% shorter because I was able to coalesce or remove duplicate error handling code. And there was no measurable performance cost for this network-bound program, even though I'm keeping track of important things to do at runtime stacks. You might think this will slow me down a lot, but it hasn't as far as I've been able to measure. My second example was with Sun's Pet Store. This is everyone's favorite J2EE application. I wish we had some more. It's loosely like Amazon.com, but you buy dogs instead of books. There's dog supply chain management in the background, yada, yada. Most importantly, from my perspective, over the course of 3,900 requests in an externally supplied third-party workload, it raises 150 exceptions. Why? Because it doesn't handle these database resources very well. Along some paths, it forgets to free them. Okay. So eventually, it tries to allocate more, and this underlying JDBC library says, no, we're out of those, and raises an exception that no one in Pet Store catches. The middleware operating system layer, JBoss, catches the exception, restarts the database, restarts Pet Store, feeds the saved copy of the request to Pet Store again, and this time Pet Store gets the right answer, but it takes loosely forever. So the average response time is high, and the standard deviation is even higher because every once in a while we spend a long time thinking about this. Again, it's about 35,000 lines of Java. There are about 120 places where I changed their code. This time I tried to do it as fast as possible to show that this is sort of easy and intuitive. It's not like trying to convert the whole program to use linear type system. So this only took about 2 hours of work. And in general, they had 3 simultaneous resources, so they would have needed 3 nested try finally statements. Again, the program was slightly shorter. The new version, because it's careful to free these database objects along all paths, raises 0 such exceptions over the course of 3,900 requests. The average response time goes down, but perhaps that's within the noise. The standard deviation does go down. Hold on. So I claim that the program is more consistent and perhaps more reliable. Yes, sir?
Change line is only 1 line. This is very high program productivity, like 1 line per minute. If the change line is bigger, it's higher. If the change is only 1 line, the change is about 2 lines. For instance. Yeah, so it's possible that I knew both the program and the thing really well. I also had...
to the West factor here, right? So let's say like some times X for a typical developer. Still.
Yeah, okay, maybe if I code as fast as I talk, then you can factor that out or something. Yeah, this was helped minorly by... at the beginning, I grepped through for a list of places where all of the bugs were, and then I had my editor set so that after fixing one, I could just say go to the next window, and it would go to that file on that line. So we've somehow factored out the cost of actually locating the errors in this metric. So that might also help. Unclear. Yeah, high programmer productivity, okay, maybe 12 hours of work, unclear. Okay, so I claim my language feature, it's kind of handy, but as yet, no one is actually using it. Either for such a language feature or for using an analysis like this to find mistakes, it would be handy if we had more notions of what the program should be doing. Thus far, I've just been using my 4 favorite specifications: sockets, files, streams, database logs. It would be great if we could automatically come up with specifications. Nominally, they can be used for pretty much anything. Program understanding, refactoring, documenting, they're the panacea of the ages. I'm actually, yes. Okay. So in Aaron Brown's undo code, previously he had been using something like, or he had been using actually this, I will have int f equals 0 and then this switch statement. And there I took the acquire and I took the release and I matched them up with a compensate action. So I moved the code from here to there. I had an explicit compensation, and for him they were sort of complicated. Writing a compensating log record, sending a network packet, something like that. For this one, since I had changed the interface, it was as simple as removing the calls to close in many cases and then just leaving the rest of the code alone. Right? So here it was automatic. In the first one I was given it and I had to move it. Okay. Yes, yes. Okay, so it'd be great if we could automatically mine specifications. They could save the world. I'm actually not going to use them to save the world. I'm just going to use them to find bugs. My goal is to try and find defects in software and then fix them and thus make the world a better place. Right? So I want to make it easier to use this sort of bug finding approach. I want it to be easier and more automatic. In the specification mining problem in general, you look at a trace of your program. You've inspected it either statically or dynamically with some instrumentation. The trace is a sequence of important events, maybe method invocations, maybe assignments to important variables, maybe information about errors, that sort of thing. And you want to automatically learn one of these, say, finite state machine policies that I've shown. Unfortunately, Jim Laris and others will demonstrate that this is an undecidable problem. It's very difficult to learn specifications. Right? So we're going to approximate things dramatically. Some approaches to approximating the specification mining problem involve learning specifications with sort of probabilistic weights on the edges, or you use frequency information. I'm not going to go that route. Instead, in a bit, you'll see that I will abstract away, or I will approximate the sort of specification that you can learn and use that to get traction. How does my specification miner work? It's based on, surprise, surprise, insights about exceptional situations, how programs deal with runtime errors. Right? It's important to me to have a specification miner that scales well. It should work on 1 million lines of code, and that requires no annotations. This is of personal importance to me. Rumor has it that Microsoft programmers are willing to annotate their code, especially if they're using something like prefast or whatnot. In my personal experience, programmers outside have been less willing to annotate their code. I want to make the burden to entry, the cost of adoption of this, as low as possible. I don't want someone to have to go through and mark up their code with a bunch of places in order for me to learn specifications about it. When I do produce candidate specifications, I want them to be easy to understand. You should be able to just sort of look at them and say, that's right or that's not. I don't want you to have to debug a finite state machine by removing edges, because I have reason to believe that that's difficult to do. Finally, and perhaps most importantly for me, I want this to perform well in that once I've learned a specification, I can feed it to a bug finding tool like ESP, say, and then actually find a bunch of bugs with it. I want to improve software quality. So I did a bunch of experiments to compare all available specification miners on one single example where the answer was known, and also to compare our specification mining algorithm against another automatic miner, one from Stanford, and against my 4 by-hand library specifications from before, those again about sockets and streams and database handles. How does this specification miner actually work? I'm going to simplify the world by only trying to learn specifications that have this shape, exactly these 3 states and these 2 edges. Right? So this sort of reduces the problem to trying to learn important event pairs A and B. In some sense, trying to learn the open and close of your program. Maybe you've called them something else, acquire sync, release sync. Right? Once I've done that, I'm going to present multiple candidate specifications to the user. Each one of them is going to be quite simple. Is it the case that open should always be followed by printf? You say no. Is it the case that open should always be followed by close? You say yes. Later, I can stitch together these smaller specifications to form bigger specifications, and I'll show an example of that in a bit. The key example for why this approach actually works is that I use an extra bit of information or an extra feature when I'm doing the learning. I classify the traces as either normal traces, where the program behaves as expected, or exceptional traces, where there's some sort of runtime error and the program does not behave as well. How does that play out? I'm trying to find these events A and B, open and close, but in general, they can be very far apart. You do the open, and then you do all this work. Presumably, you're actually doing something with this resource that you're acquiring. You acquire this lock, and then you actually change some variables that it guards. However, after an error, the cleanup code is typically less cluttered, and it just concentrates on program correctness. In the middle of a catch block, you typically don't email grandmother, you just close the socket. Right? So I'm going to divide the traces into 2 worlds, normal traces and exceptional traces. An exceptional trace is one in which at least one method call terminates with the raising of one of these exceptions, right? Some sort of runtime error. And my intuition for this miner is that I want to find event B, close, somewhere in your exception handling code, maybe in a catch block, in a finally block, in a finalizer. If we're looking at a normal trace, I expect the programmer has gotten it right. We'll see open followed by close sometime later. However, based on my previous experiments, in the presence of exceptional situations, I expect that at least once the programmer will make a mistake that we'll see open with no paired close. And this will allow us to get some leverage on the specification mining problem. Does it work well in practice? Yes, or so I'll claim. Here on the left, we've got a bunch of Java programs and how big they are. The blue column, which I'll return to in a bit, is the results from our specification miner. The next column shows the number of bugs that I found using my 4 handcrafted specifications. And on the right, I have another specification miner, that of Dawson Engler from Stanford, to compare against. How do I interpret these results? In general, we looked at about 1 million lines of code, and my specification miner produced 650 candidate specifications. Each one is very simple, of the form, must session factory.open session be followed by session.close. And you look at it and you say yes or no. Of those, 70 ended up being real specifications. The others were must open be followed by printf. You say no, that's not a real specification. If I take those 70 specifications and I give them to Monovir and ESP and we check them against the program, we find 430 methods where you make mistakes with those application-specific resources. If instead you use my 4 handcrafted specifications, you find far fewer bugs per line of code. And if you use other competing approaches, you find many more false positive specifications. You have to wade through quite a lot in order to get to the gold at the bottom of the barrel. And when you use those specifications, you don't find as many bugs. For me, what? Interestingly enough, my bugs per line of code metric for my running Dawson's algorithm is higher than what he reports in his paper. Yes. Yes, this is his a 2001 paper, Bugs as Deviant Behavior. Yes, yes, in fact. So his paper has a bunch of great ideas stitched together with no information about how to implement them. There's a section at the end, it's like section 8.2 or something, where he talks about specification mining for A must be followed by B. There he says, oh, I mined these specifications in the Linux kernel. I found this many bugs in the Linux kernel, that sort of thing. Using his algorithm on this Java code, I found more bugs per line of code than he did. So just, yes. This is entirely possible. Yes, I can't control for that. Yes. But based on talking to him about how to implement his algorithm, I would like to believe it's not that I have replaced his algorithm with some ineffectual algorithm that always returns 0 or something. I believe this is what he's supposed to be saying. Yeah, he tried to give me his code. He said, I will be happy to give you my code. And then he carbon copied all of the people at Coverity, and they immediately replied with, what are you saying? You can't give him our code. We're very sorry. So instead, he gave me a bunch of emails saying, this is how you would implement my code, and especially this is how you do hierarchical Z ranking. That never happens. Yeah, so I re-implemented his algorithm. In addition, his algorithm was for C, and I'm doing Java, so blah, blah, blah. Right. Okay, but once you have the traces, that's not such a big deal. Other questions while I'm here? No. This false positive rate of, I don't know, 1 in 9 is higher than I would like. Ideally, and in my previous work, I would like 0 false positives. Okay. Can't quite get, what?
I have a question.
Yes, Monovir.
So, the 2 data points here, one that you're finding more real bugs, and things like that, and 2 that your noise ratio is better.
Yes.
They're both due to the fact that you try to distinguish the exceptional cases from the normal. Is that
I believe so, yes. Yes. That I'm using this extra information or leveraging this other insight or something. Ah. Yeah, I skipped over it. It turns out that there are other key differences between my algorithm and his algorithm, some of which have to do with, for example, software engineering. If you do this algorithm naively, you will be led to believe that almost everything in the world should be paired with printf. Why? Printf comes up a lot, especially in error handling code. You're writing out this logging, that sort of thing. I make the explicit assumption that A and B should be from the same package, right? So if my JDBC call and system.printf, I'm not going to claim are related. If it turns out that your JDBC library and your naming library have a specification in common, it's probably that there's a glue layer that's been written on top of them, and I can find the specification there, right? So I'm going to use package level encapsulation. Yes? In my memory, that's not what he's finding in that paper. Right, right. I may. Yes. Just 4? Okay, yes. Fair enough. Yeah. I may well be misrepresenting him. My apologies in advance if I'm doing that. Right. However, compared to some other algorithms, I don't want to look just within one class. There are some algorithms out there that will say, oh, I will find all the possible orderings of methods that can be invoked on the abstract list iterator class, say. And it has been my personal experience that there are a bunch of specifications that span classes, especially if you're using the factory design pattern, say. My session factory gives me a session which must later be closed. Those involve methods on 2 different objects. I get it from the session factory, and then I close it at the session level. So I want to link things that are too far apart, but not too far apart, so I use package level testing. There's also a minor difference in how we track values. So if you just do this trace, you also want to make sure that you're looking for specifications that are about the same sort of object. For example, you might, although this never actually happens in practice, be manipulating 2 sockets at the same time, but slightly out of sync. And at that point, I might mistakenly learn the specification open, open, or close, close, or something like that. In order to avoid that, often we use some data flow information. I want to make sure that the values that are involved in A are also involved in B. My rules for that are slightly different than his. Okay.
But do you go to local analysis because in the end you're only going to feed this to something that's local?
The analysis is
You're
local.
not trying to learn about A's and matching B's with different functions. You're trying to learn about A's and B's that match within the code of the same method.
So I can apply it to my bug fixing approach later.
Exactly.
Yes.
Right?
Yes.
And that affects your
Presumably. Yes. Yada, yada, yada. Okay, I skipped ahead. Okay, finding bugs by specification. Other questions about this? False positive rate. It's too high, at least in my mind. I would like it to be lower. It's, in some sense, the lowest that I've seen in this regard. And developers that I've talked to have said, oh, I'm willing to page through 10 candidate specifications if they're all this easy in order to find one that will get me some bugs. But I'm not willing to look through 100. So this seems to be scraping the borderline of acceptability in that regard. Okay. So we found 800 bugs before. We have 400 bugs now. That's a lot of bugs, or maybe not, but I think it's a lot of bugs. And you might at this point ask, are these bugs important at all? Maybe Wes has reinvented lint, and he's finding a bunch of bugs that nobody really cares about, and they would just rather, shut up these warnings. In general, measurement of that is beyond the scope of this work, but it's something I'm interested in doing in the future. I have a few data points here to try and help this out. One is that I sent off a bunch of bug reports to a bunch of people when I found the bugs. In general, these go into the void, and I never hear from them again. But I did hear again from the Ptolemy 2 developer who was willing to rate all of the bugs that I presented to him on his own personal made-up scale of 1 to 5 stars. And here, 45% of my bugs got 4 or 5 stars, and were definitely a bug in code that's used often or more often, and he fixed it that day. Okay. I also did a time travel study. I said, can I do this on a bigger program? I took Eclipse 2.0 out of CVS. I ran my analysis on it. I wrote down all the bugs on a piece of paper. And then I looked at Eclipse 3.0, and I checked to see how many of those bugs had been fixed naturally by their development process. I did not talk to the Eclipse guys or share my bugs with them. Turns out that 43% of the bugs that I found in 2.0 would have been fixed naturally by 3.0, so slightly under half, right? And this is also an analysis that I claim generates no there are no actual false positives in some sense, but even if all of these things are actually bugs, sometimes developers don't end up fixing them. So that's important to state as well. Okay, few comparisons are available, although rumor has it that Trishul is very good at getting high numbers close to 50% in this area or 100% on small benchmarks. Findbugs from University of Maryland, and I'm working with them to add my analysis to their suite of tools on their financial application, was close to 16% here. And internal IBM tools that I'm not supposed to mention by name or by number are close to 10 to 25%, or so they report or don't report or something. Questions about this? Okay. So that's what I've done up to this point. What would I like to do in my copious spare time? Well, I claim that finding bugs is pretty easy, and what should we do now? And personally, I think that the interesting parts of the story come before and after we find the bugs, right? In general, to me, it's very important to make these things easy to use. I want my tools to scale. They should all work on 1 million lines of code. They should require minimal guidance. It's my personal belief that if programmers are willing to annotate, they're willing to annotate very little, or they'll tell me 1 thing in 10, but I can't expect them to mark up every line of code. So having a small number of false positives is important to me. In general, though, I would like to start before the bug finding problem and say, what are important bugs? What sort of bugs should we be finding? What should the program have been doing? And I've done some work in specification mining, but I'd like to do a bit more. I'd like to help the programmer fix the bug, and as a direct extension of what I've presented, currently I give you this compensation stack tool, but is there some way I could make it easier for you to use these to fix your program? I also believe that when we finally present these bugs at the end of the day, we're not necessarily presenting all of the information that we could, or that there are more things that we could say to make it clear how to fix the problem. And finally, I'll talk a bit about my sort of approach in general. Okay, so far, if you give me your Java program off the shelf, I can mine program-specific specifications. I can use those and my library specifications. I can check your program for violations. And I can even give you this potential tool, compensation stacks, to fix these problems. But despite this, the world is not a better place, right? So I'd like to do even more of these steps for you, or at least present them as options. So drawing on notions of a region inference, dependency and escape analysis, possibly the theory of reduction, left movers, right movers, I would like to automatically suggest where to put these compensation stacks and which resource to associate with which compensation stack. So it's kind of like refactoring your program to add destructors, which you can't currently do. The sort of Scylla and Charybdis problem here is that I want to make sure I don't free the resource too early. If I free it while you're still using it, then that's really bad. I also don't want to free the resource too late. This is kind of like doing region inference, Toft and Talpan, and ending up with one region around Maine. That's kind of not helpful, kind of like using a garbage collector. And the goal of this line of research, aside from the interesting analyses that I'd have to do, would be to lower the cost and time and effort to actually improve software quality with this sort of technique. So now I can find the bugs, but how can I help you actually fix them? I would also like to find some other way to explain them to you, right? So it turns out that the output of a bug finding tool can often only be understood by graduate students working on that particular project. Yeah. I believe that the backtrace may well be the wrong abstraction for explaining bugs, or it may well be an insufficient abstraction for explaining bugs, and I'd like to do more. Typically, when you have a tool like this, you present a backtrace that's just like using Visual Studio, right? It says you call foo, you call bar, you go to line 3, you take this if, and then there's a mistake. So we try this, and then I talk to the small developers that I have access to, and they say things like, in the presence of multi-threaded programs, this backtrace is very complicated. I would like something abstracted. Or, I did not actually write this code. Someone wrote this code 20 years ago, and I'm just here, and I feel scared about changing any of this, and I don't understand your backtrace. What? Yeah. This is true. And the third thing that I commonly get is, I don't understand the mistake at all. What is a race condition? I say, oh, it's a race condition. What is a race condition? Okay. Yes. So in addition, I'd like to present something based on the invariants that the programmer understands, or diffs of how the tool would fix it, right? And so this would build on some work that's done here. Yes?
If this guy gets good before that, if you make it concrete enough to see it in a photo, I will expect these programmers to understand. Maybe I'm wrong.
I would take issue with your slide. I don't agree with you at all, because
Ooh, I love it.
in our experience here, right,
Mm-hmm.
we show thousands of traces to developers every month, and they get looked at and fixed, and it works really well. And the reason it works really well is because, as Gideon said, it's a really concrete, step-by-step thing. It mimics what people go through in debug. The thing is, real programmers, unlike some of us, continuously live in a debug.
Yes.
Right? So it's a very natural experience for them, right?
Okay. So it's entirely possible that I'm talking to a lower class of developer outside of Microsoft. I don't have access to
a higher class in some sense, or a different class, right? They think differently than
different class, right? Before I started this, I would have believed exactly what you said. I said the backtrace is perfect. We have all these values. How can you not go there from here, right? And I was surprised to encounter developers who said this backtrace isn't good enough. I don't know how to fix it. Yes. I would to some degree mention them half and half. Most of the developers that I'm talking to here are staff members, as it were, at places like Berkeley or Stanford who have been hired to maintain these projects, so they live somewhere between grad student and actual developer. Maybe this puts them in actual grad student rather than actual developer, depending on how you make this distinction. I would claim that depending on the complexity of the specification, if I'm using Manuel's IRP specification, even if you give me a backtrace to the point where you're making the mistake, it might not actually be clear how you should go on from there.
No, how to go on is hard, but
I'm not having trouble convincing people that there is a problem. What I want to do is help them fix it. Yes.
right. If you there's a problem, have them understand what the problem is.
Right.
And then help them figure it.
I look forward to crashing and burning trying to do 3. So in general, if you present to me the code on the left, rather than saying there is a bug on line 4 if you don't take the if statement, or there is a bug on line 3, I would like to suggest in addition, oh, and here's a diff. This is what it would look like if your program were no worse with respect to the specifications you've given me and happier with respect to this particular error report. And for the intra-procedural case, I have ideas about how to do this, and I can talk to you if you're curious. I want to stay away from claiming I'm an error-correcting compiler. I'm not going to force this on you. But we have seen, and again, this is outside of Microsoft, but when people submit bug reports to, say, the Linux kernel developers, if the bug report is accompanied by a diff, even if the diff is wrong, the odds of some real diff actually being checked in to address the defect are dramatically higher. Okay. I'm also interested in doing machine learning and combining it with bug finding. There's been a lot of recent interest in using statistics to deal with false positives. Personally, in some sense, I believe this is the wrong approach. Yes?
I've seen too many spell checkers give people the wrong correction and they just click on it. Every time you put it, the error detects exactly wrong.
So that you can't just apply it?
Without putting your
That all you do have to do optimization, right? You do it with the mandate. And obviously there are some situations where you can mandate things, but there are a lot of situations you can't. But you have a piece of software that accepts it, you block it, and that is done. Then you don't have to solve it.
Fair enough, but I have no experience with that sort of thing as of yet. So. People are often tempted to use statistics, frequency information like the Z statistic to rank things to avoid false positives. In this particular domain, at least, that can often lead you astray. The frequently executed path probably isn't the one with the bug. And when I tried to, I mentioned this earlier, when I tried to reproduce Dawson-Engler's claims that using the Z statistic to rank things was beneficial, I found that using the Z statistic to rank candidate specifications was no better than a random shuffle. Instead, I would like to combine sort of programming language domain knowledge and non-statistical machine learning approaches. For example, imagine that I'm working with a developer, I present 10 candidate bugs to them, and they end up fixing 4 of them and not fixing 6 of those. I'd like to cluster or classify those based on programming language level features, like where in the type hierarchy were you, or was this a recently changed file, or was this in a third-party library, right? And use those discovered rules both to rank or classify bug reports that I'm presenting with the ones you're likely to fix on top, but also to guide possible future PL design work. So far, my programming language design has been fairly conservative in that it fit in exactly with Java. If I were to do something more dramatic, I would want to have a notion of what actually leads to bugs in practice and then try to address that as a first-class citizen. I'd also like to... Yes?
The first part we're already doing it. Get the developer feedback, do the ranking,
Yes.
and then use it to actually develop the technical.
Yeah. So I'm interested in trying language design at least once. As a grad student, if you make a new language, exactly 0 people, including yourself, write programs in it, right? So from a pragmatic perspective, my language features were similar to existing languages. I would be tempted to do something in which program reliability was a sort of a first-class citizen, but I would want to make sure I was addressing real areas for reliability and not just things that I think not living in a debugger are important. And this would be one way to get at that. Almost profile-driven language design, something fun like that. I'd also like to move some of what I've described online to make detection and possibly later correction decisions at runtime, but that's farther future work. Okay.
By online, you mean not
Yes.
on the web.
No, yeah, sorry. By online, I mean like online machine learning. Yes, rather than passing over the data once at the end, assuming you're getting new data points as time goes by. Okay. Loosely, in some sense, my big question is, why are we not in Fiji, right? So if the average cost of a post-deployment bug is $1,800 perhaps here at Microsoft, $10,000 at IBM, and we find 1,000 bugs and half of them are fixed, why am I not scuba diving now, right? And to some degree, I think all of the answers to this question open up interesting research areas. So one possibility is that we are finding the wrong bugs. Maybe I'm finding bugs that are really cheap or they're, something like that. And specification mining can help address that. It's possible that the bug reports I'm spitting out aren't trusted. If that's the case, then I need to work on false positives, right, which we've seen has been a problem. Maybe the developers don't understand how to fix the bugs, so the cost of even having this information that it's on line 3 doesn't actually save you much over the customer reporting it by the phone. That's why that's why I'd like to work on better explanations or better potential fixes. It's possible that it's too labor intensive. Even if I tell you that you've made a mistake using I/O request packets in Windows device driver, maybe it still takes you eons to implement the fix. Wouldn't it be nice if we had PL features or better language design to legislate away classes of these mistakes? And to some degree, I think that we need better metrics for this line of work. I see bug finding research today as where alias analysis was 5-ish years ago. You publish a paper, I can do 1 million lines of code in half a second, I can do 2 million lines of code in a nanosecond, that sort of thing, and you report points to set sizes. These days we seem to report, oh, I can find 500 bugs, but were they fixed? Do we care? Were they important? We don't know. Are we actually making the world a better place by being PL researchers and doing this, or should we instead take all of our summer interns and just hire them into the testing group? Would that actually make the world a better place? I don't know, but I'd like to find out, right?
So okay, I have to take issue with you again.
Yes, Manavir.
I think you're
not being provocative.
you asked me to be a shill during your talk, right?
Thank you, sir. I appreciate it.
I think you're a little disadvantaged because of where you are right now. Because I would claim that at Microsoft, a lot of this is happening, right? We do file and fix hundreds of bugs every month. In real products that matter a lot, and the bugs are deeply important. And you could argue we're not a PG because management is not paying us enough for doing that, but we are. So,
I guess my response to that is, I wish I were at Microsoft. How do I? Outside, I can't see it.
We're not getting paid enough. As you said, we're not a PG, right? So,
Have you that problem, and are they disproportionately being probably done for things? And I think that's probably true. I think
Right.
the amount of effort and value people put into this kind of technology is not as much. There should be partly because they're not under attack. You know, they're not attacking Java systems, they're not attacking Linux systems yet. But
Right.
As the heat goes up, so will the cost.
Right. It's possible that I wouldn't observe this problem in the real world, but thus far I've only been able to do research from the ivory tower.
no, and as Ben said, the Microsoft is one more part of it.
You also forgot the other, or like the renewable sources, but fixing is
Yeah.
not going to necessarily get
Fair
If,
enough.
There's just more people who test That's a good thing.
That's true.
But that's the practical result.
At which point, language design and tool support becomes only more important. Can we make sure that when you're writing new code that it's somehow better?
Well, this is practical. It's good for that.
Yes.
If we're all writing in template code, then
It'd be tough.
Right.
Okay. Okay. What a scary thought. Anyway, I think there's fun stuff to do there. How does this work in general? It's not clear that I will always be a white box program analysis, I can find bugs sort of guy. What's my general approach to this? There was one area that I was interested in, program reliability, and we found a specific feature that we thought needed attention, error handling exceptional situations. We did some measurements, some analyses to actually see, is this actually a problem? Are people making mistakes in their error handling code? Is this a big part of reliability? And then we proposed some solutions to address it that in some sense rearrange static and dynamic features. Maybe before you had 2 statically nested try finally statements, now I'm going to keep track of some of this at runtime. And I believe that in general this is applicable to sort of other common features, either reliability or domain specific. Maybe later I want to look at components, configuration management, parallel programs, something fun like that. This is how I go about it. Oi, finally done. What have I talked about? I've claimed at the beginning that handling exceptional situations is error prone, and I backed that up with a static analysis and a fault model that found 400 or 800 mistakes in 4 million lines of code. I proposed a new language feature and showed some case studies that showed that it didn't add an unbearable runtime overhead. It wasn't difficult to program, and that in some cases it can make programs more reliable. I presented a novel specification mining algorithm. I used it to find 400 additional bugs in 1 million lines of code. In general, it was more useful than my by-hand specifications. And my future work, I'm interested in sort of preventing, explaining, and fixing these bugs. So that is the part of the story that comes before and after actually doing the analysis. Any questions? Any additional questions? Manavir, surely you can attack me in some other way. Is that a, Ben? Yeah?
So, getting rid of finalizers, you would recommend
There's a trick with finalizers, and I'm not the first person to make this argument, but if you have a finalizer or if you have cleanup code for an object, it's almost invariably because someone else can see the object. If you have a table that only you can see, you don't need to call close on it because when you're done with it, no one else can check that. So it's almost always shared resources. If you then have finalizers and it's a shared resource, you're probably using some sort of access control to get at it, like you're implementing your own lock table, that sort of thing. So you need locks to get at this resource. Finalizers are, by specification in languages like Java, they execute in a separate thread, the garbage collection thread or whatnot. you can run into places where if you take all your cleanup code and move it to Finalizers without paying attention, you can add concurrency bugs to your program, right? You can suddenly deadlock. I'm in the Finalizer, I'm feeding this object, I want to acquire this lock to change this table entry, but I can't because I've interrupted the code that already had the lock. In that regard, yes. If we were in some magical fantasy world where the operating system and the programming language, perhaps we're in some VM or language runtime where these things are more tightly coupled, right? Or where the garbage collector understood resource categories, then it might well be possible. If I'm talking about file handles and whatnot, if the operating system could somehow say to the JVM, oh, I need more file handles, why don't you go try and collect some, then it might be reasonable to have file handles. Modulo that sort of science fiction future, I would recommend destructors and destructor-like things instead in almost all cases. Does that answer your question? Yeah. Yes. Right. 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 C, I'm not as fond of. If you like, if you like C++, I can give similar examples, but you also have exceptions in C++. Right. For C, I can imagine generating similar traces and doing similar specification mining by instrumenting the program to check all of the return values that you're not checking and then flagging that in some way as part of my trace. So I can see the specification mining. The actual bug checking, to some degree, I think that work at Stanford may already have well covered this area. Dawson Engler, among his many hidden papers, has a bunch where he looks at how you check return values and whether all the clients of this particular interface believe that you have to check the return value or not, and if you don't check it, then something is wrong there. For finding exceptional situations, at runtime, if you're willing to give me other information that tells me when it's an exceptional situation, then I don't necessarily need language level exceptions. For example, imagine that you've annotated the program to keep track of certain metrics, like how many requests you're getting per minute or what the average in-node density of the heap is, right? And if you can tell me that it should normally be 400 requests per minute and now it's 4,000, if I take that as an exceptional situation, then I could either fix things or try to learn specifications online, by which I mean at runtime, even without language level support. But I would need some other flag that's telling me we're good now, we're bad now. Does that answer your question, or did I? Sort of. Okay. Other question? Thank you all.